All right, now that you have seen that first exercise, done that first exercise yourself, um, let's look at the definition of a quadratic function and also a few examples. And a quick reminder with these example videos is they go a little faster than lecture in class. Remember to pause and rewind as much as necessary, and mark spots you don't understand with a question mark to remind yourself to ask for help later. All right, so first of all, a quadratic function is a function that can be written with a value of a not equal to 0 in this form. Like, so the a, b, and c are just numbers. So so as long as your function is written f of x equals a number times x squared plus a number times x plus a number by itself, then it is a quadratic function. So, and this is called standard form of a quadratic function. Okay, so the ax squared is called the quadratic term. Having x being squared in the function is really what makes it quadratic. So this is the quadratic term. Bx is called the linear term because linear functions have like a number times x, like the slope times x. And c is just called the constant term, because as x changes, the c part does not change. So just as a quick example, let's write these precisely in standard form and state the values of a, b, and c. So f of x here, this is the same f of x as exercise 1 that you already did, by the way. F of x is 2x squared, so it already has the ax squared part, but then it doesn't have a bx, but you can still write it as 0 times x. 0 times x is the same thing as having nothing there. And then plus c is plus negative 5. So this is now written in exactly in standard form so that you can see that a is 2. That's what you have multiplied by the x squared part, the quadratic coefficient, you can call it. The b part here is 0. And the c, in this case, is negative 5. All right, so that is the values of a, b, and c that go with this one. With g of x, you have to FOIL it out, which I already did a minute ago in the last one, but we can do that again here. We're going to get g of x is, I'll leave the negative 2 alone for now. Do the x times x is x squared, minus 2 times x is minus 2x, plus 1 times x is plus x, and then 1 times negative 2 is minus 2, and you can then combine these two terms to become minus x, and then distribute that negative 2 in there, and you'll get g of x equals negative 2x squared plus 2x plus 4. All right, so that is now written in the standard form, and you can see what the a is. The a here is negative 2, b is 2, and c is 4. Okay, so that's that. Now let's look at example 2. How does the value of c affect the graph of f of x equals ax squared plus bx plus c? You might already know the answer to this, but let's just go back here in case you're not sure to see, like, let's look at this one. With f of x equals 2x squared minus 5, the value of c was negative 5 here, right? And where did that negative 5 show up in the table? Well, when you plug in x equals 0 here to get this result, you did 2 times 0 squared minus 5. And 0 squared is, of course, just 0. 2 times 0 is 0, so that just gives you 0 minus 5, which is negative 5. So the value of c is the result that you get when x is 0. And with this other one here, the value of c was 4 here, right? That's what we got here as well. So with c equals 4, where does that show up in the graph? It's right here. When x is 0, the y is 4, because 0 squared is 0, and multiplying anything by 0, like this whole part, multiplying it by 0, or plugging in x equals 0, makes the whole thing become 0. So you just get 4. And let's see how that shows up in the graph. Well, if x equals 0 and y is negative 5, that's a point on the y-axis. So that's going to be the y-intercept. And here you can see the y-intercept is right here. You got x equals 0 and y is 4 for that one. So anyways, that's what the value of c does. It is the output of the function when you plug in 0. Because I'll write this all out here. A times 0 squared plus b times 0 plus c gives you 0 plus 0 plus c. So f of 0 is just c. And how does that show up on the graph? That is the y-intercept. Okay, so now let's talk about, on the next page here, how can you tell if f of x equals ax squared plus bx plus c opens upward or downward? So let's look at this one. This one opened upward. This one opens downward. Like the opening is on that side. Here the opening is on the top side. So that's what we mean by that. And what is it about these equations that you could use to tell that that's what's going to happen? That's something we're going to investigate here. So this is going to get a little technical. Let's start with 1 point. Well, we know what we're going to get when we plug in 0 into this. Just like we explained up here, you're going to get f of 0 is always going to be c. So that's going to be 1 point on this graph. I'm just going to, maybe, I don't know if c is positive or negative. Maybe this is your value of c. Maybe c is a negative number down here. But that's 1 point that's going to be on the graph. Now, let's say that a, the coefficient of x squared, is a positive number. Then let's say, so a is positive, and then you plug in a very large positive number for x. Like, let's say x is 1,000. So if x is like 1,000, then you're going to have, when you plug that in, the ax term, ax squared term, is going to be this positive number a times 1,000 squared plus whatever b is times 1,000, and then plus whatever c is. So which one of these is the largest of the three terms here? So the largest one, well, 1,000 squared is 1,000,000. So you're doing 1,000,000 times a plus 1,000 times b plus c. And as long as b is like less than 1,000, then 1,000 squared is going to be bigger. And if b is really big and a small, then instead of plugging in 1,000, plug in x equals 1,000,000 or x equals 1,000,000,000, something bigger than b. So the largest of the three terms is always going to be ax squared if x is a really big number. And is that positive or negative? Well, let's see. We're saying that a is positive and anything squared is positive. So ax squared is going to be a very large positive number. So this is going to make f of x large and positive. So that's if you plug in like something way out here. Like if you keep going on the x-axis out to 1,000, you're going to get some really, really big result up there. And what if you plug in a large negative number for x? Like something way out here, like x is negative 1,000. Then when you plug that in, well, what's the difference here? If this is negative 1,000 squared, then negative 1,000 squared is still positive, and it's still going to be about 1,000 times bigger than b times 1,000, because 1,000 squared is 1,000,000. So the largest of these is going to be the ax squared part still, and it is still positive. So this makes f of x still large and positive. So when you plug in negative 1,000, you're still going to get some really big x coordinate out here. So the moral of the story here is that if a is a positive number, then plugging in a large value of x, either a large positive number or a large negative number, makes the whole result come out to be a large number. So it's going to look something like that. Maybe if c is negative, it's going to look something like that. That's okay. It's still going to open upwards. All right. Let's look at if a is less than 0. So if a is less than 0 and you plug in a large positive number for x, then let's see, when we do this time a times 1,000 squared plus b times 1,000 plus c, we are now plugging in a negative number for a. So this is a negative times a positive. This whole thing is going to be negative, or at least the ax squared part. But it's still going to be a really big negative number. Because again, 1,000 squared is still 1,000,000, and that's 1,000,000 is 1,000 times bigger than just 1,000. So the largest of the three terms is still ax squared, and this time it is negative. This makes f of x large and negative. And by the same reasoning, if we keep going on with this, if we say a times negative 1,000 squared, still saying that a itself is a negative number, plus b times 1,000, or sorry, times negative 1,000 here, plus c, well, negative 1,000 squared is still positive. Multiplying it by a negative value of a makes the result negative. So it's still going to be the largest part, and it is going to be negative still. And this is going to make the whole thing, this really big negative number plus these other smaller numbers, large and negative. All right, so what does this look like now? I'm running out of room. Whoops, let me make a little room over here. Whatever c is, maybe c is negative, maybe c is positive, but when you plug in a big negative number for x, like negative 1,000, or a big positive number like 1,000, you still get a big negative result. So the whole thing looks like that. Something like that. So it's going to open downwards. All right, so that is the moral of the story here, is that if a is greater than 0, it's going to have to open upwards. And if a is less than 0, the whole thing opens downwards. Okay, so let's fill in these blanks with what we figured out. The y-intercept is the point 0, c. That's what you get when you replace x with 0 with c. The whole thing opens upwards if a is greater than 0. And it opens downwards if a is less than 0, which we just sort of explained here. So if a is a negative number. All right, let's look at this example to try to bring this all together here. This is this function, h of x right now, is in factored form. Let's find the x-intercepts and write it in standard form and then draw a rough sketch. Okay, so what can we do with this? So first of all, the easiest way to find the x-intercept, well, is to leave it the way it is, and let's see why. First of all, let's remember that x-intercepts are points on the x-axis, right? So if it's a point on the x-axis, then those are points where y is 0. We've got some x-coordinate and y is 0, some x-coordinate and y is 0. So that's what we're going to do, is we're going to make the output of this, the y-coordinate, be 0. So whatever values of x we get that make this equation true are going to be values of x that make the whole thing equal to 0, that make the result equal to 0, which gives you a point on the x-axis. Okay, so how do you solve this? Well, the trick is that multiplying anything times 0 makes the whole thing be 0. So this is, when it's written in factored form like this, we have two things getting multiplied together. If negative x is 0, that's going to make this whole thing be 0 times something. And negative x is 0 exactly when x is 0, so that sounds good. And this part, x plus 3 is 0. If you have a value of x that makes this whole thing equal to 0, then that's going to make this become some number times 0, which makes the whole thing be 0. And that's the trick with these. We're going to get negative 3 equals x. And we're going to do a lot more details of solving equations with this method later. But the trick is that you have two things getting multiplied. If you can make either of those two things be equal to 0, that will make the whole thing be 0. So these are the values of x that make the y be equal to 0. So we can say the x-intercepts are the points 0, 0, and negative 3, 0. Okay, sounds good. Now let's write this in standard form. So to get this in standard form, we don't want it in factored form. We want to distribute the negative x in here. So that's going to make this look like h of x equals, we're going to have negative x times x is negative x squared. Negative x times 3 is negative 3x. And this is basically in standard form. If you want to get it a little bit more precise, you could write it like this, like negative 1 times x squared minus 3 times x plus 0. So this way you can see what the a, b, and c values are. You have a is negative 1, because again, negative 1 times x squared is the same thing as negative x squared. So, and the b is negative 3, and the c is 0. So that is standard form. All right, let's use everything we found to draw a rough sketch of this. I should probably make it bigger. It's a good habit to make your graphs larger than you think you need to. It's a lot easier to see what you're doing that way. Okay, so I'm going to start with let's just use these facts here. The y-intercept is 0, c. In this case, what is your value of c is 0. So that should be 0, 0. Which is right there. Okay, so that also agrees with the x-intercept that we found before here. The x-intercept and the y-intercept is the same for this one. So we've got that. And what else do we know? What's the value of a? A is negative 1. So what does that tell you? -1 is less than 0. So because of that, it should open downwards. So whatever we get, we're going to have something opening downwards. We also know one point that we found. We got the point -3, 0. So let's draw that over here. There's -3, 0. And if that's all we knew is these 2 points, and we know we're going to draw a parabola, which is what the graph of quadratic functions look like, it might look like this, or it might look like this, or it might look like this. But we know out of these different things, the one opening downwards is the one we want. So we're going to draw something opening downwards, and that is a good enough sketch for this problem, because it says a rough sketch, and that's what we got. We got, using the information we got, we know it's opening downwards. We got the x and y intercepts right. That's a decent graph. And this is going to be an important kind of problem. There's going to be a lot of problems in chapter 3 that are like this, where you have to find the x-intercepts, and you need to know whether it opens upwards or downwards. It's going to be a thing we're going to use for a lot of different kinds of problems. All right, so next up, you have some exercises, 4 different exercises, which are the same kinds of instructions as these. Give these ones a shot. Do your best. If you get stuck on one, it's okay to go on to another one, and I'm going to post the solutions to these on the next exercise video after this.